Hi, uh, I think I'm going to be alone today. I hope you're all safe and healthy. Today we're going to talk about polynomial rings uh, and some concepts about irreducible and prime elements. Let me start with my first question, and of course I'm going to publish it anyway. Let R be a commutative ring with one different from zero. It's zero additive identity. Suppose that for each A in R, there exists an integer n greater than 1 such that a to the n is equal to a. Okay. Under this condition, we are going to prove that every prime ideal is a maximal ideal. Then prove that every prime ideal of R is maximal. For this one, we are going to take a prime ideal. We start with taking a prime ideal. Let I be a prime ideal of R, and we are going to show that for the maximality of R, we are going to look at the quotient of R by this I, and we are going to show that this quotient ring is a field. We show the maximality of I by showing that R over I is a field. Okay? Now, and for this one, of course, we have to find the multiplicative inverses of each element in R over I. Okay? Now let A bar, which is A plus I, be a non-zero element. In R over I. Okay? Now by assumption, for this A, for this element A, there's an integer greater than 1 such that A to the n is equal to A. There is n greater than 1 such that A to the n is equal to A. So let us take the nth power of this A bar. Then A bar to the n is equal to A plus I to the n, which is nothing but by the multiplication in the quotient ring, A to the n plus I, but we know that A to the n is equal to A, so this is equal to A plus I, and this is A bar. So this means that we have the same kind of equality for the elements in the quotient ring. Okay? So what we have is that from this equality, A bar to the n minus A bar is equal to 0 bar. 0 bar is the additive identity of the quotient ring. So let us take the left-hand side into A bar parentheses. This is if and only if in A bar parentheses, A to the n minus 1 bar is equal to 0 bar. Okay? So what we have is that here, since yeah, okay, Now, what we know is that as I is a prime ideal, if we consider the quotient ring, that's an integral domain, right? And this means that R over I, and so R over I has no zero divisors. But we have an equality here. We have two elements, A bar and this term here. Product of these two is equal to 0 bar, right? But since we have no zero divisors, as R over I has no zero divisors, and of course, A bar is different from 0 bar, which is just I. This means that A bar to the power n minus 1 bar has to be equal to 0 bar, okay? So from here, we are going to obtain the inverse of A. Now we have A bar to the power n minus 1 is equal to 1 bar, and this is if and only if we take A bar to the out times n minus 2, this is equal to 1 bar, okay? So what we have is that, or we can write it in the other way around, A bar n to the power minus 2 times A bar is equal to 1 bar, okay? So this implies that A bar to the power n minus 2 is the inverse of, is the multiplicative inverse of, A bar, and so R over I is a field. Okay, R over I is a field means that hence I is maximal. I is a maximal ideal. Okay? Okay, this is it. Now, second question. Okay, let me check my notes here. Our second question. Okay, this is about irreducibility of a polynomial. Second one. For each positive integer n, prove that the polynomial this is very special polynomial, x minus 1, x minus 2, and we can define it for every n, x minus n minus 1. This polynomial is irreducible over z. Is irreducible over z. Okay, our question is this one. Now for this one, first we are going to assume that the polynomial is reducible. Assume that x minus 1 times x minus 2 times x minus n minus 1 is reducible. And it can be written as a product of two polynomials, f of x and g of x. X minus 1 dot x minus n minus 1 is equal to f of x times g of x for some f g in the polynomial ring over integers. Okay? Now, if we consider this polynomial and evaluate it at the values from 1 to n on integers, then we get some equality. First, notice that since we assume that our polynomial is reducible, then this means that the polynomials f of x and g of x have degree strictly less than n. Okay? Let us note down also such that degree of f and degree of g is strictly less than n because of the reducibility, the assumption of reducibility of the polynomial x minus 1, x minus n minus 1. Okay? Now, now evaluating the polynomial, at x is equal to 1 to n, we get what? F of k times g of k is equal to minus 1, okay, for k from 1 up to n, okay? Now, after that, what we know is that since f and g are polynomials whose coefficients are coming from integers, those values of f of k and g of k are all integers. Okay, let us note it down also, as f of x and g of x are from z of x, f of k and g of k are integers. This means that we have a product of two integers, and the multiplication is equal to minus 1. So we have some knowledge about, have some candidates about the values of f of k and g of k. Okay? So what we have is that either we have f of k is equal to 1, which is equal to minus g of k, or f of k is equal to minus 1, which is equal to minus g of k. Okay. Now, from this point, we are going to consider a polynomial. Consider h of x, which is equal to f of x plus g of x. Okay. The sum of these two polynomials, and since we are in the polynomial ring, coefficients from integers, and since we know that the degree of these two polynomials is strictly less than n, then we know that the degree of h is strictly less than n. Okay? As, let us note it down also, as degree of f strictly less than n, degree of g strictly less than n in this polynomial ring. Okay? But we know that if we evaluate h over k, k from 1 up to n, what we have is that f of k plus g of k is equal to 0 for k from 1 up to n. So we have found at least n different roots of this polynomial h, right? Thus, h of x has at least n roots. But this is a contradiction. Why is that so? Because we know that the degree of h is strictly less than n, so it cannot have n distinct roots, right? However, degree of h of x strictly less than n, hence we get a contradiction. Right? So this means that so we must have h of x is just a zero polynomial. Okay? And this gives us f of x is equal to minus g of x. So by using this knowledge, we can rewrite our original polynomial. So x minus 1, the polynomial x minus 2, x minus n minus 1 is nothing but minus g of x squared, right? If you remember, it was equal to f of x times g of x. So we have found that f of x is equal to minus g of x. So we can write our polynomial as minus g of x squared, okay? But if you compare the leading coefficients, the leading coefficient of the left-hand side, this is equal to 1, right? But the leading coefficient of the right-hand side is negative. So in this case, these two polynomials cannot be equal. Okay, so we get the contradiction, hence our assumption is false. This means that our polynomial x minus 1, x minus n minus 1 is irreducible over z. Okay, so this is also done. What about our third question? Yeah, here. Now we have a PID. If you remember, a PID is an integral domain, all of whose ideals are principal. Okay, principal means that the ideal is generated by just one element. Okay, now the third question is that let I is it I? No, is it R? Let R be a principal ideal domain. Let me call principal ideal domain. Again, this means that PID, this means that every ideal of R is principal, that is generated by just one element. And let A be an element of R, be a non-unit irreducible element. Okay? Now we are going to show that if we take an irreducible element in a PID, it generates a maximal ideal. Then show that the ideal, this one generated by A is a maximal ideal. So this is the crucial information that over PIDs, irreducible elements generate maximal ideals. Okay? Now suppose that we have an ideal I between our ideal generated by A and the whole ring R. Suppose that there is an ideal I such that we have this inclusion I, this one, R. Now we are going to show that I is either equal to the ideal generated by A or has to be the whole ring R. Okay? Now since R is a PID, since R is a PID, that is every ideal is principal. This means that being an ideal of R, I has to be principal, right? I is a principal ideal, and there exists there exists B in R such that I is just the ideal generated by B. Okay? Now what we have is that since A is an element in the ideal generated by A, as A is in the ideal generated by A, and this is contained in I, which is the ideal generated by B, then we can write A as a multiple of B. Then, no, not then, A is equal to B times C for some C in R, right? So, but we know that A is an irreducible element. It was given in the question, right? A is an irreducible element. This means that either B or C is a unit, okay? Since A is irreducible, either B or C is a unit in R. Now, if B is a unit, if B is a unit, then we are done. Why is that so? Since the ideal contains a unit, it means that it contains the multiplicative identity, and it has to be the whole ring. Then I is equal to R. If not, if C is a unit, if C is a unit, then there exists C prime in R such that C times C prime is equal to multiplicative identity. Okay? In this case, A is equal to, no, what we have is that in this case, B is equal to B times 1, which is equal to, instead of B, 1, I'm going to write C times C prime, B times C times C prime, which is equal to B times C prime, okay? But B times C is equal to A. We have written it where? We have written it here, okay? So this is nothing but A times C prime. So in this case, in the case of C being a unit, B is a multiple of A, right? So this means that B lies in the ideal generated by A, and so all of the ring I lies in the ideal generated by A. Okay? And so I lies in the ideal generated by A, and we have the other side of the equality already. So this means that I is equal to A. Okay? So in each case, we have reached the conclusion. We have started with an ideal between the ideal generated by A and the whole ring R. And in each case, if B is a unit, we have found that I is equal to the whole ring R. And the other case, C being a unit, we have reached that I has to be equal to the ideal generated by A. And this means that there is no intermediate ideal between the ideal generated by A, which is an irreducible element, and the whole ring R. So giving the fact that, giving the conclusion, the ideal generated by A is maximum. Okay? Now that's all. This is also important because it is very useful. Okay, our last question here. In this question, we are going to use the maximality of the ideal generated by irreducible elements, and we are going to construct a field, okay? And this construction is always valid. You can always use it to obtain finite fields. Now we are going to write down our question. Let F3, which is actually Z over 3Z, be the finite field of order 3, be the finite field of order 3. Now consider the polynomial ring. Consider the polynomial ring. Over F3. Okay, and the ideal and the ideal I and the ideal I, yeah, which is generated by x squared plus 1 in F3 of x. Okay, now we are going to prove that F3 of x over the ideal generated by x squared plus 1 is a field, and we are going to determine the order of the field. Determine the order. Okay. Now we have a field, and then we consider the polynomial ring of over field and an ideal of it. And then by using this polynomial ring and the ideal generated by a specific element, we are going to construct the field by taking the quotient. Okay. Now in your video lectures, it is shown that if you have a field and if you consider the polynomial ring over the field, then that polynomial ring is a PID, okay? Done in video lectures. If F is a field, then f of x, yeah, is a PID. A PID. That is, every ideal is generated by just one element, okay? And by the previous question, we know that irreducible elements over PIDs generate maximal ideals, okay? By the previous question, we know that over a PID and irreducible elements generate a maximal ideal. Okay, now for this one, we know that F3 of x is a PID for our question, as F3 is a field. F3 of x, the polynomial ring over F3, is a PID. And we have a polynomial, right? Now consider the polynomial, which is the generator of our ideal I, x squared plus 1. Let me call this f of x. Okay. Now our claim is that it's an irreducible element. Okay. Claim f is irreducible over f3. Okay. Now, since it is of degree 2, it is enough for us to just look at the roots of f of x, x squared plus 1 over f3. As f is of degree 2, it is enough to look at the roots of f over f3. Okay? Now we have only 3 elements in F3, so this means that it is enough to look at f of 0, f of 1, and f of 2, which are all elements of F3. And f of 0 is nothing but just 1, different from 0. F of 1 is equal to 2, which is different from 0. And f of 2 is equal to 4 plus 1, 5. This is 2, different from 0. Okay? So we have no roots of this polynomial over F3. So there are no roots of f of x, which is x squared plus 1 over F3, and hence x squared plus 1 is irreducible over F3. And this means that the ideal generated by x squared plus 1 is maximum. Hence, I, which is the ideal generated by x squared plus 1, is a maximal ideal of F3 of x. So if you take the quotient, then you're going to obtain a field. Hence, we have a PID and a maximal ideal. We are taking the quotient. This means that the quotient is field. If you remember, I is maximal if and only if R over I is a field, okay? And I is prime if and only if R over I is an integral domain. Hence, F3 of x over the ideal generated by x squared plus 1 is a field. Okay? Now, what about the number of elements in this field? Let us take a representative. We are going to count all the elements, just direct calculation. Okay? Let an x to the n, an minus 1 x to the n minus 1, plus a1x plus a0 plus the ideal generated by 1 is an arbitrary element from this field. Okay? The coset representative here, this polynomial, let me call this one as g of x. No, not g of x, h of x. Okay? Now, remember, we can apply division algorithm here. So let us divide this h by our generator x squared plus 1. Okay? Divide the representative h of x by x squared plus 1. Then what we have is that h of x is equal to x squared plus 1. Then let me write this way. Then there exists q of x and r of x in f3 of x such that h of x is equal to x squared plus 1 times q of x plus r of x, with r of x is equal to 0, or what? 0 or 0 less than or equal to degree of r of x strictly less than degree of x squared plus 1. Okay? Now, we know that since the degree of r is strictly less than the degree of x squared plus 2, which is equal to 2, this means that r of x is at most a polynomial of degree 1. Okay? So, r of x is something like ax plus b. Okay? A and b are coming from F3. Okay? Now, from this equality, if we take those as the coset representatives, We can write this one as h of x plus the ideal generated by x squared plus 1 is equal to x squared plus 1 q of x plus r of x plus the ideal generated by 1. Okay, this is I'm considering these two elements, these two sides of the equality as the coset representatives. Okay, and this equality is in the quotient ring as 3x over the ideal generated by x squared. Okay, but we know that since this part is a multiple of x squared plus 1, this part lies in I. Okay, so what we have is that h of x plus the ideal generated by x squared plus 1 is equal to, this is inside I, means that the right hand side is only r of x plus the ideal generated by x squared plus 1. So this means that every coset representative can be also represented by a polynomial is of degree at most 1. Okay, this is a x plus b plus the ideal generated by x squared plus 1. So count the possibilities for the coefficients a and b. We have 3 possibilities for a and 3 possibilities for b. This means that we have in total 3 times 3, 9 possibilities for this polynomial, okay, r of x. So let us write it in words. Okay, so every element of the quotient ring f of x over the ideal generated by x squared plus 1 is represented by a polynomial of degree 1 or 0. Okay, for the polynomial r of x which is equal to ax plus b, we have 3 possibilities for each a and b. Okay, so this means that, and so we have 3 times 3, 9, 3 to the power 2 different coset representatives. Okay, this means that since we have 9 different coset representatives, we have 9 elements in our field obtained by taking a quotient of a PID by an axiom ideal. Okay, hence a 3x over the ideal generated by this one has 9, which is 3 times 3, 3 to the power 2. It is better elements. Or let me write in the field of 3 to the power 2. Okay, these are all of my questions for today. I hope to see you next week. Okay, bye.